Now we're going to learn how to apply the ideal gas law to chemical reactions like we would in laboratory conditions. So, in reactions in which we have a gaseous reactant or product, the amount of gas is often specified in terms of volume, given a temperature and pressure. And we can use the ideal gas law to convert pressure, volume, and temperature to moles. Because remember that N, which is the number of moles, is PV equals or divided by RT. Okay? And then we can use the stoichiometric coefficient in our balanced chemical equation to convert to other quantities in the chemical reaction. So let's do an example to see how that works. How many moles of ammonia are formed by the complete reaction of 2.5 liters of hydrogen at 381 K and 1.32 atm? Assume there's more than enough nitrogen. So remember, the first thing that we want to do is write our balanced chemical equation. We have H2 gas combined with N2 gas to give us ammonia or NH3 gas, okay? And so let us just make sure that this is balanced. We'll put a 2 here and a 3 here to balance that out. Okay, so now we have 2 nitrogens and 6 hydrogens. So that's good. All right, so now we got our balanced chemical equation, the most important part. And then we want to use the information given. It looks like we're being asked how many moles of this do we have if we took some hydrogen, but we're not given the moles of hydrogen. We're given the volume of hydrogen to be 2.5 liters. We're given the temperature of this hydrogen to be 381 K, and we are given the pressure of hydrogen to be 1.32 atm. So this is what we're talking about, how since we're not given the moles, we're given all these other conditions, V, T, and P, and of course R is the gas constant. We know that we can solve for N. So let us solve for N. N is being PV over RT. And since our R here, let's write that up here, is 0.0821 liter atm per K mole, let us make sure that all of our units are in the units for R over here. So pressure, is that an atm? It sure is, so I can go ahead and plug that in. Perfect. Now, is volume in liters? Yes, it is, so I can go ahead and plug that in. And, of course, my R is 0.0821 liter atm per K mole. And my temperature, is it in Kelvin? It sure is, so that works out perfectly. So look at this. My liters cancel, my atms cancel, my kelvins cancel, and I'm left with moles, and that's what the unit for N should be. So let me go ahead and plug this in and see what I get. Alright, let's do everything on the top. 1.32 times 2.5, and we're going to divide that by the bottom, but let's put that in closed parentheses on the bottom. And so you should get N to be 0.105, or since we just have 2 sig figs here, let's call that 0.11 moles of what? Hydrogen gas. That's what we're trying to figure out. Alright, but the question asks us how many moles of NH3 here. That's what we're trying to find out. But since we figured that part out, we can go ahead and now set it up like we've always learned how to do it in the beginning. We have 0.11 moles of H2, and for every 3 moles of H2, I produce 2 moles of gas. You see how I'm going back and using my balanced chemical equation. So moles of H2 is here, moles of NH3 is on the top. Now we just use my stoichiometric coefficients. And this cancels, and I'm left with moles of NH3. So 0.11 times 2 divided by 3 should give me 0.073, and that is moles of NH3. And so I've solved that problem. Alright, go ahead and give this one a try. How many liters of oxygen gas form when 294 grams of potassium chlorate completely react in this reaction? And this is the reaction used to ignite fireworks. So this is the reaction here. Potassium chlorate solid gives us potassium chloride solid and oxygen gas. And I'm trying to figure out the volume here, and I'm given the conditions that the oxygen gas is collected at a pressure of 755 millimeters of mercury at a temperature of 305 K. And I'm given that there is 294 grams of potassium chlorate. So I'm trying to figure out the volume of the oxygen gas here. And notice I can use the ideal gas to find the volume of oxygen gas because it's the only one that is actually gaseous state. I can't use the ideal gas law for solids, can I? So how do I go about this? Because it looks like to use PV equals nRT, I need N, and I don't know what N is for oxygen here. What is N? The number of moles. Well, as we've learned previously, you can figure out what the number of moles of oxygen is based on how much you have here. And so you have 294 grams of potassium chlorate. And remember, you can go from grams to moles of potassium chlorate, and let us find out what the molar mass of potassium chlorate is. That would be 122.55 grams of potassium chlorate for every 1 mole of potassium chlorate. Then now I can use my stoichiometric coefficients, and I can see that for every 2 moles of KClO3, I produce 1 mole of oxygen gas. So there you go. I just figured out what N is. Okay? 294 divided by 122.55 times 2. So that was 1.20 moles of oxygen gas. So there you go, 1.20 moles of oxygen gas. Now that's good. Now I can solve for V here. So V is going to be nRT over P. And N over here is 1.2 moles of oxygen gas. R is, remember, 0.821 liter ATM per K mole. Perfect. Temperature is already in Kelvin, so check. 305. Fix that here. And pressure is, pressure looks like it's in millimeters of mercury, whereas it should be ATM. So let me do that over here. 755 millimeters of mercury. And remember, for every 760 millimeters of mercury, I have 1 ATM. So 755 divided by 760 is 0.993 ATM. Perfect. Now I can plug that in. 0.993 ATM. So let's see what cancels out. My moles cancel, my Kelvins cancel, my ATMs cancel, and look at that, I'm left with liters. And my original problem asked me for how many liters of oxygen gas do I produce. So perfect. Let us do the math here. 1.2 times 0.821 times 305 divided by 0.993. And so you should have gotten 30.3 liters of oxygen gas are produced from 294 grams of potassium chlorate. So, there's these special kind of conditions that allow you to go directly from moles to liters. And those conditions are at STP, standard temperature and pressure. And this is very important that you know these terms, STP, and the values of those terms. So the standard temperature is 0 degrees Celsius or 273.15 Kelvin, and the standard temperature or pressure is 1 atm or 760 torr. Okay? And if you run a reaction at these standard temperature and pressures, you can bet your money on it that 1 mole of any gas will take up a volume of 22.4 liters, granted that you are running your reaction under STP conditions. So this is a shortcut, if you will. If you are running the standard, the reaction under standard temperature and pressures, you can have a direct conversion factor between moles and liters. And again, this is 1 mole of any gas. So it could be 1 mole of hydrogen gas, it could be 1 mole of oxygen gas, or it could be just 1 mole of air mixture. At standard temperature and pressure, that 1 mole of gas will take up 22.4 liters. Very important conversion factor. 1 mole will take up 22.4 liters. Let us see how we can use this conversion factor. If we have to calculate the number of liters of a gas that forms at STP when 0.879 moles of calcium carbonate undergoes the following reaction. So here's my reaction for calcium carbonate. It breaks down to give me calcium oxide solid and some carbon dioxide gas. But here's the key point here. This reaction is at STP, so I don't have to do it the long way where I have to use my stoichiometric coefficients to find out how many moles of carbon dioxide have. Then I figure N, what N is, and then I plug it into my ideal gas law. I don't have to do that because this is at STP conditions. So if I have, okay, so let's see how we would set that up. We would have to see that we started out with 0.879 moles of calcium carbonate solid, and for every 1 mole of calcium carbonate, I produced 1 mole of gas, CO2 gas, right? And since this is a gas, I know that at STP conditions, 1 mole of my carbon dioxide gas will take up 22.4 liters volume. And I'm being asked to calculate the amount of liters of carbon dioxide gas produced. So that's good. I've reached that. I can cancel these out. I've used the stoichiometric coefficients just to see how much gas that I produced, how many moles of gas that I produced. So 0.879 times 22.4, and so this is 19.7 liters of CO2 produced, CO2 gas. Now I want you to go ahead and give this a try on your own. How many liters of oxygen at STP are required to form 10.5 grams of water according to the following equation? And this is our equation for forming water. We have hydrogen gas combined with oxygen gas over here to give us 2 moles. Now, the key point here again is this reaction is done at STP, standard temperature and pressure, and I have 10.5 grams of water being produced. So how many liters of oxygen did I have to use to get this 10.5 grams of water? Well, since this is at STP conditions, I'm going to go ahead and do 10.5 grams, and I'm going to go directly from moles to liters using the molar volume. But given this in grams, so I have to take the grams into moles. And for every 1 mole of water, I have 18.02 grams of water, right? And then for every 2 moles of water produced, I needed 1 mole of oxygen gas. All right, perfect. And see, since this is a gas, this is oxygen gas, now I can use my molar volume because I don't want the moles of oxygen here. I'm being asked for the liters. And what is my direct conversion factor between moles and liters? That's my molar volume of any gas. So this is a gas. I'm going to use its molar volume. 1 mole takes up 22.4 liters. And I'm going to reread the question. The question says, how many liters of oxygen? So perfect. I'm good. I don't have to do any more conversions. Be careful, because sometimes I might ask you, how many milliliters do you need? All right, so let's do 10.5 times 22.4 divided by the 18.02 times 2 in closed parentheses. So this gives you 6.53 liters of oxygen gas that were needed in order to produce this 10.5 grams of water.